Alright everyone, this is Brock Skaggs and I'm making the second video here. In our first video we started on this truss problem where we were intending to use the method of joints in order to solve for the axial force carried by each member, also calculate the stresses, and solve for the reactions. It's kind of a secondary part of it. And so the video is getting a little long, so I cut off the first video here when we completed task 1, determining the reactions at joints A and E. And so if you are kind of getting this midstream, you might check out that video if you have any questions on that. And we're really going to go into task 2 now, where we're going to look for calculating the normal stresses experienced by each truss member. And so before we can calculate normal stresses, we're going to have to actually calculate the forces carried by each of the members itself there, because hopefully you're familiar with trusses. They're formed with two force members. The members themselves are assumed to be in pure tension and compression. And with that, we have a formula that we can use to calculate the normal stress, and that's right there, sigma is equal to F over A. Well, the area part is just the cross-sectional area of the truss members themselves, and so that's given for us here. I said it was 2 by 2 by a 1/4 inch wall thickness square tubing, which has an area of roughly 1.59 square inches, and I'm getting that right from the SolidWorks Weldment library. But the force carried by each truss member, well, that's something that's not apparently given, right? I know that the load P hanging way out here to the far right end of the truss is 5,000 pounds, but that doesn't mean that each one of the members is carrying 5,000 pounds. And so we need to use some statics here in order to come up with the force carried by each member itself. And so we're going to emphasize using the method of joints in order to solve for the forces, and then from the forces we can then solve for the normal stresses. And so method of joints, what's that all about? Basically the method of joints is about inspecting the truss joint by joint, drawing a free body diagram isolating the individual joint itself, representing the members pulling or pushing on that joint by the forces that they're carrying, and then writing equilibrium equations just for your small free body diagram, which is just of the joint itself. And then we should be able to work our way around the truss joint by joint in order to solve for all of the forces associated with the axial member, or associated with our truss members. And so where do you start on this? Well, you've got to start with a joint that has at most two unknowns, because here we're thinking of the joint as a specific point in space, and so we have basically two equilibrium equations for these 2D problems. You can write the sum of the forces in the x equation, sum of the forces in the y equation. Really, you don't have a moment equation, because since you're just talking about a point and not some larger rigid body, there's no way to have that perpendicular offset distance in order for the forces to try to cause that rotation. And so here I've actually got two different choices that I can make. One thing I could do is look at joint E over here. Joint E is only connected in by two members, and I know the reaction force E sub x already, and so that would just have two unknowns. Or I could go in and look at joint C here on the far right hand side. It's only connected by members 2 and 3, and so either one of those would be ways to start off this problem. I'm going to go ahead and start at joint E since I've already went ahead and solved for the reactions. And so I'm going to draw a free body diagram of joint E to start off my method of joints. And so here we are. Again, FBD is my acronym for free body diagram, and I'm looking at joint E. And so here I'm just going to draw a dot. That dot right there represents joint E. And so now the question is, what forces are acting on joint E? Well, one of them is the roller, right? We've got the roller here pushing on the wall, and it's going to be pushing to the right, it appears, with a magnitude of 15,000 pounds on joint E. And so here, I'll go ahead and use red for my force vectors. This is our E sub x, which from our earlier part of the problem, we found that to be 15,000 pounds. And so next, what do we have? Well, we've got members 5 and 4 here tie into it, and so we need to say, hey, these things could be pushing on it, they could be pulling on it, I don't really know at this point, but something could be happening there. And so I've got to represent those with a force, and so I'm going to have F5 and F4 is what I'll call it there. I notice F4 is the horizontal one, excuse me, and so I will go ahead and draw it this way, and F5 is the vertical one. And notice on those two, I'm drawing them with the arrowheads directed away from the point itself. Basically what that does is assume its intention. And so with that, I'll go ahead and illustrate that here. Say I'm looking at member 4 here. Well, if member 4's intention, then it feels like it's being pulled apart. And so I'm going to draw that with those arrows feeling like it's stretching member 4. Well, there's Newton's third law. It says, right, action, reaction. So if it feels like it's getting pulled apart, then it's going to impose a force on joint E that's going to be pulling in the opposite direction, and joint D also pulling in the opposite direction that it feels like it's being pulled. And so that's why those components, looking at the free body diagrams, will it be E and D, are pointing to the inward side of things, if you will, is associated with member 4 being in tension itself there. And so that's the way I always draw them. Here I can just kind of look at it and say, yes, this thing's going to be in compression, but I like to always think positive values in tension, negative values in compression, and that's why I always assume the force vectors coming out of the joints in the positive tension direction, if you will. And that way I let my equilibrium equations work out the negative sign for me. And so that looks complete for joint E as far as free body diagrams go. There's joint E. I've got the forces associated with each of the members, and I've got the reaction force there, which is looking good. And so now I'm ready to write equilibrium equations. I've got two equilibrium equations I can write, some of the force in the x and some of the force in the y. I'll start with the x. Again, adopting the usual convention, positive x to the right, positive y vertically. And so here I've got E sub x plus my F4. It's got to equal 0. Well, just looking at that, that's going to say F4 is equal to negative E sub x. It's very simple algebra here. And so F4 is negative 15,000 pounds. And so what that's telling us is that F4 is actually in compression and has a axial force of 15,000 pounds that it's carrying there. Also it says, hey, that arrow there that I've drawn an F4 on my free body diagram actually is pointing to the left and not the right. The sum of the forces in the y here. All I have is the vertical F5 and no other forces moving in the y direction. So it's saying F5 is actually equal to 0 pounds. That's called a zero force member when you're doing these truss problems. And it's like, hey, that's weird. It's not carrying any force. So yes, I could actually remove that from the member itself. In this situation, yes, but I could say, hey, what if I put a load here, downward load at point E there? Then I would need it there in order for it to work out for us. And so this is, and this loading condition is having no load carrying at the zero force member, but I could dream of a different loading condition where I could change that very easily. And so now I've figured out the forces carried by each of the members 4 and 5. And so we know the axial force carried by this guy and this one. And so now we got to hunt down another joint where we would have two unknowns. I'm just going to look right up here at joint A. I know 5 is 0, and 1 and 6 I don't know. I know the reaction's here. The only other thing I'm going to have to do is I'm going to have to find this angle theta here, but that's easily doable with a little trig. And so I'm going to draw a free body diagram of joint A next. And so I'm coming in here, free body diagram of joint A. And so again, just drawing a point. There's joint A. Here we had A sub x and A sub y at joint A. Well, we're still going to be needing to be represented here. Those are the reactions associated with the pin connection at the wall. So here's A sub x. Here's my A sub y. Notice I'm just using the same directions that I drew in my free body diagram in the entire truss. F5 we said had a magnitude of 0 for the forces carrying, so I'm just going to leave that one off, and then I'm going to assume 1 and 6 are in tension here. And so that means I'm going to point the arrows away from my joint. And so there is F1, there is F6, and our angle theta is this guy right here. And so before we can write equilibrium equations, we need to be able to decompose F6 into its horizontal and vertical components, basically saying how much went to the right and how much went downward. And so to do that, we need to figure out that angle theta. And so this angle theta here, hopefully you can kind of see the right triangle formed by members 1, 7, and 6 here. And so I could use something like the inverse tan and say opposite over adjacent, or L2 over L1, in order to solve for theta, which is exactly what I'm going to work through here. I'll say theta is equal to inverse tan, and which one was the opposite? It is L2 over L1. So inverse tan here, L2 over L1. L2 is 4 feet, L1 is 6 feet, so basically 4 over 6. Length units are going to cross off here. And so inverse tan of 4 over 6, roughly 33.7 degrees there. All right, so now we're ready to write our equilibrium equations. And so let's scoot over here. Let's go ahead and do the vertical component first. And so I've got the sum of the forces in the y. The reason I'm doing it first is because my unknowns, F1 and F6 is going in both the horizontal and vertical direction, while F1 is only going in the horizontal direction. So if I write my vertical equation first, the only unknown will be F6. And so first, starting with what's pointing up, well, I've got a sub y pointing up here. It's just strictly vertical, so the entire magnitude's going up. And F6 here, though, only a portion of its total magnitude is going in the downward direction here. And so it's going downward, so I'll put negative. I can say, well, F6, but I only need a part of F6, not the complete vector F6. And so I need to look at the vertical component. Since my angle theta is here, it would be F6 times the sine of theta. And that would equal 0, because we are thinking that this joint is in static equilibrium. And so now what do I need? Well, I need to solve for F6. And so I'll just kind of scoot over to the right here. Solving for F6 out of this is going to equal AY over the sine of theta. And so AY, that was 5,000 pounds, I believe, is equal to P. And we'll divide that by our sine of the angle 33.7 degrees. And so give me just 1 second in the calculator. 9,013.9 roughly. It is a positive value, so F6 is in tension. All getting back to how I assumed the arrows representing the force vectors to go in my free body diagram. So that's looking good. And now F1. And so F1, we can solve for that using our horizontal equilibrium equation associated with these forces. And so we'll say sum of the force in the x. Well, we got a sub x here going horizontally, plus F1, that's also going horizontally. And then it'd be plus what? F6 times the cosine of theta now, because I want only the horizontal component of that vector. And we'll set that equal to 0. And now I'm after the F1 magnitude. So just solving this for F1. What do we have here? We'll kick everything else to the right, so it'll be negative a sub x minus F6 times the cosine of theta. So a sub x, that's one I don't have off the top of my head. A sub x was here negative 15,000 pounds. And so I'm going to write this in here as a negative of a negative 15,000 pounds. Where's the negative and the negative come from? Well, the first negative is this negative sign right here that came from the algebra. So it's a negative. The second negative is coming from the fact that I pointed a sub x in the same direction in this free body diagram as I did this one, so that I can substitute the exact value that I got here, the negative 15,000 here. And so I just take that, that was negative 15,000, throw that in there. Notice it's going to become a positive value. Minus our F6, we just solve for that F6 value, that's the 9,013.9 pounds, times, in parentheses, so we don't get confused, the cosine of our angle, 33.7 degrees. Here, I might be able to split that in there fairly close. Let's see what that value is. 15,000 minus the 9,013.9 times our cosine of the angle, 33.7. That's actually equal to 7,500 7,500 pounds. And so here, oops, 7,500 pounds. Notice it's also a positive value, so direction is assumed correct on this free body diagram as far as the arrow goes, and it means that it is in tension. So now we got 1 and 6 done. We are motoring right along across this truss here. And so there's 1, and there is 6 there. So at this point, I'm actually going to make a jump here, and let's look at joint C here next. So joint C, just looking at the way the angles are going to work together, that is also going to be angle theta. That's the 33.7 there. At joint C, I'll have the one downward force at P, and then I would have the reaction, or not the reaction forces, but the forces carried by members 2 and 3 there. And so one thing, if you're watching this video and trying to learn this method by itself, this would be a good point. You could pause it actually, try to draw the free body diagram, get the equilibrium equations, solve for F2 and 3, and then just play the video and see if you get it right. So I'm just going to go on though. We're looking at free body diagram of joint C here. And so what did C have? Well, there's the point that C, it did have the force that externally applied load P hanging down here with a magnitude of 5,000 pounds straight down. And then we had a component that tied in horizontally, another truss member that went off at this angle here, and we had an angle of theta, that theta being the 33.7 in between. So what were those forces, or those members called? 3 and 2, or 3 is the horizontal one. So we've got F3 here and F2 up here. So at this point, hopefully you're kind of picking up on the motions of this process here. We're just writing the equilibrium equations again. We've got 2 equations, sum of force and sum of force in the x, sum of force in the y. In this case, I'm going to start with the y because F2 is moving in both the horizontal and vertical directions, and F3 is only going horizontally. And so sum of force in the y should only have one unknown here. And we need the vertical component of F2. Just by the way that angle is drawn there, it's F2 times the sine of theta minus P. Everything is in static equilibrium here, so we're setting it equal to 0. And now we're solving for our force F2. So F2 is equal to P over sine theta. P was 5,000 pounds. Substituting in our values. Theta was 33.7 roughly. And we'll see what we have here. Well, that's the exact same thing we wrote before. It's right about 9,013.9 pounds there. So 9,013.9 pounds for F2. And then we solve for, what, F3 using the horizontal equilibrium equation. So sum of the forces in the x, let's say negative F3. That one's moving off to the left. Then we'd also have minus the horizontal component of F2, right? Because a part of it is moving in the horizontal direction, so, or directed in the horizontal direction, not really moving, so to speak. But minus F2 times the cosine now of theta. Notice P doesn't enter into this equation because it's only moving vertically, not horizontally. And so now we're solving for F3. And so looking at this, F3, what do we have here? F3 would be equal to negative F2 times the cosine of theta. And so negative F2, that's negative the 9,013.9 pounds. So negative here times our cosine of theta. And we'll see what we have. So negative 9,013.9 times our cosine of theta, negative 7,500 pounds. And so F3 is actually going to be in compression, carrying a force of 7,500 pounds. There we go. So knocked another 2 out, numbers 3 and 2. And so I'm just kind of keeping track by making the circles here. I've now got 2 here, 3 here, and really I'm just looking at number 7 there is the only one I'm missing. And so I'm going to draw a free body diagram of joint B just because it's a little less busy than joint D. It's only got 3 members instead of 4 members there. And we'll solve for that force. And so free body diagram joint B. Hopefully at this point you're seeing the pattern of the process. Here I've got 3 forces to deal with, 1, 7, and 2. One's horizontal. And again, I'm always going to assume their intention for the way I like to do it. F1 here. F7 goes down. F2 is at some angle here. I need to find a way to decompose F2, so we need an angle. Here, what is it, alternate interior angles, because that's going to be a horizontal line here, so this angle is actually theta as well, and so I can use that. So that angle is theta, so that'll help us decompose F2. And really in this free body diagram, F7 is the only thing I don't know, and so I'll just go ahead and write a vertical equilibrium equation to solve for it. And so sum of the force in the y direction here, it would have negative F7 minus F2. It would be times the sine of theta for the vertical component. That would have to equal 0 because everything is in static equilibrium. So we have F7 is equal to negative F2 times the sine of theta. So negative F2, F2 being 9,013.9 pounds, times the sine of our angle, 33.7 degrees. And out comes negative 5,000 pounds there. I think it's exactly 5,000 pounds, yes, if you don't round off the angles or your intermediate values. So I'll just put equals negative 5,000 pounds. What that's telling me is member 7's carrying a force of 5,000 pounds. The negative says that this arrow is actually pointing upward, which to me means that the truss member itself is feeling compression there. And I believe we've got all the axial forces at this point, right? Just kind of looking at it, we have 1, 2, 3, 4, 5, 6, and 7 of them, which should be good. So we are done with calculating the axial forces carried by each member, but we're after the normal stresses experienced by each member, because if I knew the stresses, then I could start talking about how close things were to plastically deforming and those type of good things. Well, in the previous video I talked about, hey, after I find the force carried by each member, I can use this formula here in order to calculate the normal stresses. That sigma is equal to F over A, where the area is the cross-sectional area again of each of the members. That's given up here at 1.59 square inches, and the force is the force carried by each member, and so that's why we had to go through the method of joints in order to figure out the actual force that was carried by each of the members. And so in order to speed this part up, I'm just going to use Excel here. I'll make a very simple table. We'll store the area here. It's 1.59, I believe, inches squared. Just pulling up a little bit to you. Then we'll have a table which will have the member, it'll have the force in pounds, and then we'll have the normal stress in PSI, that's sigma value. And so here the force, or the members, we had 7 of them, so we called them 1, 2, 3, 4, 5, 6, and 7. For the forces, member 1 here, if I'm looking through my calculations, F1's right here, it was 7,500 pounds. Member 2, 9,013.9 roughly. Member 3, right here, negative 7,500 pounds. Member 4 was near the top, negative 15,000 pounds. Member 5 here was next. That was the zero force member, so it's not carrying any load at this point. 6 is 9,013.9 roughly as well, positive. And 7 is the last one, it was negative 5,000 pounds. Here I'm going to assume, or I'm making the sign convention that if I have a negative number, it is compression, positive numbers are in tension there. And so to calculate the normal stress, there's always the force divided by the cross-sectional area. So I'll lock that cell B2 in order to allow that to drag down with us. And so there are the normal stresses experienced by the members itself here. You can see the highest one as far as magnitudes is the roughly negative 9,433 psi there. So that's how we would calculate the normal stresses. Just like last time, I'm going to go ahead and verify that a little bit by using a SolidWorks simulation. And so what I've done here is modeled the truss, ran the simulation with the 5,000 pounds being applied way out here at the far joint. And so what I'm going to do is right click and I'm going to go through and probe each one of these members. You can see kind of the flag that's popping up, and this shows me the normal stress that SolidWorks thinks it's experiencing. I think I've got one more here. Yes. Kind of move this around so we can see a little bit better. I'll hide this as well. And there we go. I believe we can see them all now. And so I'm going to go ahead and show both of these. I believe one was right here, 4719.8, 4716, 4717 really there, so that's pretty close. 2 I believe was this one, 5,672. We got 5,670 almost, so that's good as well. 3 was walking around here. Again, negative 4719, negative 4717, good agreement there. The next one was here. This was element 4. You can see negative 9433 matches up quite closely with that value. 5 was our zero force member. Notice SolidWorks showing element 5 here has 0 for the PSI value, and so that's good agreement there. 6 should be this guy here. 5,672.5, 5,670, so good agreement again between our numerical approach and theoretical. And finally, member 7 right here, the vertical one in the middle, negative 3146.5 roughly is what SolidWorks showing, negative 3144.7 is what our theoretical calculation shows there. And so notice we have very good agreement happening between the numerical SolidWorks result as well as what we calculated using the method of joints to solve for the axial forces, then a simple definition of normal stress in order to calculate the normal stress experienced by each of these truss members. And so hopefully this helps you with your statics a little bit as far as using the method of joints in order to solve for the forces inside of each truss, and then also showing an application of normal stress, because we're thinking of these trusses. They're 2 force members, idealized pin connections there, and so each one of these members are in pure tension and compression there. And so thank you for watching the video, and I hope you find it helpful.